Hello everyone, welcome to the class once again. I hope you're all doing good and you're the best of your health. So the first exercise of this chapter, that is mechanical properties of fluids, we have discussed some good 5 questions on this JEE advanced pattern questions. In this exercise, we'll be discussing the next 5 questions based upon the JEE advanced level. And also, as I've advised you, the questions are of mixed type. You'll be getting single choice, more than one choice, and even matrix match, assertion reason, and integer type. Let's go ahead with the next question of the day, that is question number 6. What force must be applied to detach two wetted photographic plates, 9 cm by 12 cm, this is what is given the dimension, in size from each other without shifting them? The thickness of water between the plates is 0.05 mm, surface tension of water is 0.03 Newton per meter. This is what is given. A 31.5 Newton, B 16.5 Newton, C 40.5 Newton, and D 20 Newton. This is what has been given. First of all, you must be thinking that how to solve such kind of question. You must have not seen till now such kind of question. But let me tell you, the force acting is equal to surface tension into length. That is what we know. Surface tension into length, that is the force acting on any part of the given surface. So first of all, let me show you how this will be. If this is the photographic plate, one plate is here, this is the other plate. Now, the water will be somewhat like this. This is the water part. Now, see that, let's say its diameter is D. Now, see, understand this is a concave curve will be formed. Between the photographic plates, a cylindrical layer of water will be formed. You can imagine, take two photographic plates, just imagine, you can take your two palms, and if it's stuck, the two photographic plates are stuck, and a water layer is actually in between them. You can imagine here as I'm showing you. Now, the portion of water that will be actually between them, that will be a cylindrical portion. It will be having a diameter. So we can comment on this radius that will be equal to diameter by 2. First of all, it's a concave part here, the concave portion will be made because we can easily say that the meniscus will be concave meniscus. Now next thing, we have to find out the thickness of water between plates is 0.05 mm, this is what is given. The surface tension of water is 0.073 Newton per meter. And what force must be applied to detach the photographic plates? Force required. First of all, the force required will be equal to the force by which it is actually attracted. The force acting due to the inner part will be given as surface tension per unit radius. Sorry, this is not force, this is actually pressure. I used force, this is actually pressure that we know. Surface tension will, pressure that will be within the inner part of the concave surface, that will be equal to surface tension per unit radius, that is what we know. From here, if I write force, force will be equal to pressure into area. This is what we know. Now, instead of pressure, we can write this as S by R into area. This is what we have reached to this equation. So what do you do? Take note till here. I'll start from the other end, take note till here. Now we need to only put the values here. We need to put the values, and you see here we need to find out the value of force. Force, if I write here, force already I have written here, the value of surface tension divided by the radius and multiply by area. So surface tension divided by the diameter and then divide by 2. So this 2 will come here and multiply with area. Let's put up all the values. Twice the surface tension, 0.073. Multiply with area. Area that will be actually enclosed, that will be taken. This area, the surface area of the plates, its dimension is given as 9 cm by 12 cm. You can write it into proper SI units. So 9 into 12 into 10 to power minus 4 square meter. Divide by the diameter, that is equal to, given the thickness, that is 0.05 mm. So this we can write as 0.05 into 10 to power minus 3 in proper meter. The force that you are going to obtain from here, just the calculation portion is left, you can easily solve them, and the answer that you will be getting after this, that you will be 31.5 Newton. This is the result that you will be obtaining. Just you solve this on your own, it will not be a problem. It will be 31.5 Newton. This is kind of question that I was willing to tell you all that what kind of question can come in your examination. 31.5 Newton, that's the right answer. Rest all options are incorrect for this. Force is equal to surface tension or pressure into area in this case, and that is what we have used. And pressure will be, one more thing you must have learned, the inner side of the concave portion, the excess pressure will be equal to S by R. Remember this. That is what we have used here. Next thing, let's go ahead with the next formula. Next question actually. A solid sphere of radius capital R and density rho is attached to one end of a master spring of force constant K. The other end of the spring is connected to another solid sphere of radius R and density 3 rho. The complete arrangement is placed in a liquid of density 2 rho and is allowed to reach equilibrium. The correct statement is or are. See, this is a question more than one choice correct. So you can get 2 options correct, 3 or 4, all the options can be correct, and even one option can be also correct. And you must be knowing how JEE actually marks on such questions. If you choose all correct options, you'll be getting +4 marks. Let's say there are 3 options as correct. Let's say B, C, D are 3 options as correct. So if you choose B, C, D, you'll be getting all +4 marks. If you choose only B and C, you'll be getting only 2 marks, +1 for each correct. But if you choose A, B, C, you'll be getting no marks for this. It will not be evaluated. And since it's a multiple choice, so negative marking is not there in multiple choice. And if negative marking is there in your examination, so if you choose any incorrect option, you'll be getting negative mark for it. So be very wise. As many options you get as the right answer, that many options you choose. Don't choose any extra option. So let's go with the question. It's saying that option number A, the net elongation of the spring is this much, 4 pi r cube rho g by 3k. B, the net elongation of the spring is 8 pi rho cube rho g r cube rho g by 3k. C, the light sphere is partially submerged. D, the light sphere is completely submerged. A solid sphere of radius r and density rho, this is the light sphere, is attached to one end of a master spring of force constant K. The other end of the spring is connected to another solid sphere of radius capital R and density 3 rho. This is the heavier sphere. The complete arrangement is placed in a liquid of density 2 rho and is allowed to reach equilibrium. See here, the case. We have a container, it's containing a liquid of density 2 rho. 2 spheres we are having. One spring is attached here. We have another sphere. Both are of radius r and r. Need not to get confused the relative size that I have drawn. Both are of same radius r in these 2 cases. I believe that you can make out what I am trying to show you here. The force constant is K, the spring constant that is given as K. Now, first thing you understand whether it is completely submerged or partially submerged. Let's comment on it. See here, since spring force will be pulling it downward. Understand? Spring force will be pulling it downward. Buoyant force will be acting on it in the upward direction, and the weight will be also acting in the downward direction. So we cannot comment anything on whether the spring is completely submerged or it's partially submerged. So what we are going to do, first of all, we are assuming that it is completely submerged, and then we'll comment at whether it is completely submerged or not. So I'm taking it partially submerged, and later on we will comment on this whether it is completely submerged or not. If our assumption is correct, it will be completely submerged. Now see here, the forces acting on these 2 spheres, its density is given as rho, and its density is given as 3 rho, and its density is given as 2 rho. The liquid density is given as 2 rho. Let me write this 2 rho at the center so that everything could be clear to you all. Now first of all, we talk about the upper sphere, sphere 1. Let's say this is the sphere 1 and this is sphere 2. If we talk about the upper sphere, the forces acting on it, its weight will be acting downward. Let's say the spring is stretched by a length x, and that is what we have to comment on, the net elongation of the spring. It is stretched by a length x. So the force acting on it, its weight for sphere 1, since both are in equilibrium, weight will be equal to, you see, buoyant force will be acting on it, and spring force will be also acting on it, and spring force will be acting in the upward direction. It's stretched, sorry, it will be acting in the downward direction. Since it's stretched, it will be acting in the downward direction. So weight plus spring force, weight plus spring force will be equal to buoyant force. This is what we can comment. Now its weight will be how much? Its volume into density into gravity. Its volume will be 4 by 3 pi r cube. Its volume, its density is given as rho, and this we got as mass into gravity, plus spring force, that is Kx, is equal to buoyant force, that will be equal to 2 rho, and then we got the density into volume, that is 4 by 3 pi r cube into g. We got this. Let's say this is equation number 1. Now for the second object, sphere 2, if we comment, you see here for sphere 2, again I am writing the net weight acting along the downward direction. It's in equilibrium. Net weight acting along the downward direction will be equal to the spring force and buoyant force, because spring will be pulling it upward. So the net weight will be equal to buoyant force plus spring force. Weight is acting on the downward direction. Its weight will be 3 rho. Its volume 4 by 3 pi r cube. We got volume density mass into g is equal to buoyant force, that will be again volume into density, that is 2 rho, multiplied with g plus spring force, that is Kx. This is what we can comment on both the two. Now you see here which term can be cancelled out and which term will be taken into consideration, and easily then we can comment on the value of x. First of all, equation number 1 and 2, if you compare and if you try to remove this portion 4 by 3 pi r cube 2 rho g, and here you are having 4 by 3 pi r cube 2 rho g, and since we want the value of x, and that the value of x will be getting in terms of r, rho and g. Let's see in what terms x value is given. It's given in terms of r, rho, g and k. So you see here what I am going to do, I am going to subtract equation number 1 from equation number 2. So 2 minus 1, if you do, and let me do at this part. Equation number 2 minus equation number 1, we will be obtaining this term 4 by 3 r cube g minus 4 by 3 r cube rho g, and here you are having 3 rho, and here you are having only rho, so you will be getting 2 rho 4 by 3 pi r cube multiply with 2 rho into g. This is, if this you take and subtract this term, so rho, and here you are having 3 rho minus rho, you are getting 2 rho, rest all terms are constant and common, so we can take that. Then again you will be getting this term, so minus kx, so let me write here minus kx, cos we have to subtract this, is equal to this term minus this term will be cancelling out, is equal to kx. So from here we have used equation number 1, equation number 2, the value of x will come out to be, you see here, this will go 2x, you will be getting 4 by 3 pi r cube and multiply with 2 rho g divided by 2k. So finally you will be obtaining the answer as 2 and 2 will be cancelled out, so 4 pi r cube rho g upon 3k. This is what you are getting. 3 will be there, so 4 by 3 pi r cube rho g by 3k. Let's see, the net elongation of the spring is 4 by 3 pi r cube rho g by 3k. Yes, this is the answer, that's matching. The net elongation of the spring is 8 pi r cube rho g by 3k. No. Option number C, the light sphere is partially submerged. Now see here, since the equation is balanced, In our case, equation is balanced, and we have taken the spring is completely submerged, and that is giving us the right equation. For the equilibrium, that has to be completely submerged as we are getting as per the response. So the light sphere is partially submerged. No, it is completely submerged that we have taken. That's right. The light sphere is completely submerged. Yes, this is the answer. So option A and D are the answer for this. So you have to choose A and D. You're getting plus 4 marks. If you choose A, D and any one, let's say you choose any one of the option more, then you're getting incorrect answer. And only 2 options will be actually the correct answer as per the given option. You can check logically also. A very good question, and this question has been asked in your previous year examination. So you will be having an understanding what kind of questions do come in your examination. Let's go ahead with the next question of the class. Question number 8. Two solid spheres, A and B, of equal volumes but of different densities, dA and dB, equal volume but different density dA and dB, are connected by a string. They are fully immersed in a fluid of density dF. They get arranged into an equilibrium state as shown in figure with a tension in the string. The arrangement is possible only if dA is less than dF, B, dB is less than dF, C, dA is greater than dF, or dA plus dB equals to twice of dF. Let's comment on, we have to comment on the value of dA, dB and dF, you have to comment. Now how they are related? You see here, let me show you the scenario. We have a container, we have 2 spheres connected with the help of a string. We have 2 spheres A and B. This is what has been given. Both have a same volume V. Let's say both have volume V. Volume of each sphere, let's take it to be V. Now you see here, the tension in the string that is going to exist, let's say it's T, and it's completely submerged. The kind of question is nearly similar to what we have done in the previous one, but see, we have to comment on the densities. First of all, B is in the downward direction and A is here. And now you see we have to comment on the densities. Already you must be having an idea because a similar question has been done. So you must be having an idea that JEE can repeat the similarity of question, can repeat the kind of questions. They're not repeating the exactly same questions, but the similarity in questions can be there. Now you see here, again if I talk about tension will be acting in the downward direction, and on this tension will be acting in the upward direction. Tension acting along the downward direction, tension acting along the upward direction. That is what both these spheres I have marked. Now they have different densities. Its density is given as dA, its density is given as dB, and the fluid density is given as dF. The fluid density is given as dF. Now comment on the equilibrium. Let's frame the equations for equilibrium. For equilibrium, what we can do? For equilibrium of A. Now clearly A is at the top end. Let us say if this is the case, the weight would be equal to its weight acting on downward direction, tension acting along the downward direction. That will be equal to buoyant force. So from here, weight is how much? Volume V. We have taken as volume as V, volume into its density dA, volume into density into gravity, plus tension T is equal to buoyant force. So volume into density of liquid into gravity. So we got this equation number 1. Clearly from this you can comment that density of A will be less than density of F. Because V and G, they are common, density of A will be less than density of F, sorry, density of fluid. So option number A is clearly we can get it from the first option, because there is tension in this string. It says that with a tension in this string. So if the tension is that is positive, so clearly you can say that dA will be less than dF from equation number 1. This can be reached, first conclusion. For second sphere, for equilibrium of A, now for B, we can write its weight is equal to tension plus buoyant force. Its weight will be equal to tension plus buoyant force. Now weight is what? Volume into its density. Volume into its density into gravity will be equal to tension plus buoyant force. Volume into density of fluid into gravity. We can write in this way. Next you see this. Clearly we can make out that dB will be greater than dF. From here, because tension is added, there is a positive value. V and G are same here. So we can comment that dB will be greater than dF. Second conclusion, I believe that you can clearly see up till this end. So dA is less than dF and dB is greater than dF. Let's see which option we are getting. dA is less than dF, that's correct. dB is less than dF, no, that's higher. C, dA greater than dF, no. Now for D, dA plus dB equal to twice of dF. How to comment on this? If you see, if we just what I'm going to do, I'm going to make some conversions and let's remove the tension so that we can compare dA, dB and dF all simultaneously taken together. Let me rub this part and let's reach on to the next part. Now see here, 1 and 2, how can we remove the value of tension from 1 and 2? Clearly we can do that if I just change the equation number 2, let's say this equation number 2, and if I write VA dBg, V dBg minus T is equal to V dF into G. This we can comment. Next you see we have to remove the value of tension. Equation number 1, if we add 1 and 2, we'll be getting VdA, and this equation number 3, okay, I'm writing equation because it's similar to equation number 2, but then too I'm mentioning equation number 3. 1 plus 3 will give us VdAg, or Vg you can take common, and dA plus dB will give you Vg as common and twice of dF, because here VdFg and here you're having VdFg. That's very simple. So dA plus dB will come out to be twice of dF. So remember in the last case also we had, if you check, the density of fluid, if you take its twice, will be equal to density of both the objects that is actually submerged. Here also we are getting same thing, density of dA plus dB equals twice of dF. Let's see, density of A plus density of B, dB equal twice of dF. Even D is also correct. Correct options are A and D in this question also. Earlier also we got A and D, here also A and D. Similar kind of question but different way to represent them. So remember such cases when come, if this is lying at the bottom end, its density will be higher. If this is lying at the upper end, its density will be lower. Sum of the density will be twice of the density of the fluids that you can make out. Next thing, then only they are going to be submerged in an equilibrium position. Let's go ahead with the next question of the class. It's an integer type, so only integer lying between 0 to 9 will be the right answer for this. A raft of wood of mass 120 kg floats in water. The weight that can be put on the raft to make it just sink is 10x kg. Find value of x given density of raft equal to 600 kg per cubic meter. So as per the given statement of the question, it says that we have a raft of wood which can float in water. So let me say that this is a raft. It's floating in water. This is what that has been given. This is water. This is raft that's flowing. Now it says that what weight you should keep so that it completely sinks. So first of all, a raft of wood of mass 120 kg floats in water. The weight that can be put on the raft to make it sink is 10x kg. Find value of x. Given density of raft is 600 kg per cubic meter. Now if a block is put in such a way, if we place a block on it in such a way whose mass is m, and let's say this mass of raft is given as mr, it completely sinks, so water level will rise. The water level rises till here and it will be completely reached till here. I'm not showing the entire portion so I can differentiate the two situations. Now the net downward force will be equal to the buoyant force. So m plus mr into g will be equal to the total volume of raft multiplied with the density of water. Let us take density of water as rho W multiplied with G. That is what we can comment. Now you see here, we need to find out the value of mass of the wooden block, of the object that has to be placed. G will be cancelled out. M will be coming out to be volume of raft multiplied with rho of water minus mr. Volume of raft will be its mass upon its density. So its mass is given as 120 kg. You see here, mass 120 kg and density 600 kg per cubic meter. Multiply with density of water, that can be taken as 1000 minus mass of raft again, so 120 once again. So from here if you see 0, 0, 0, 0 will be cancelled out. Here you will be getting 20 into 10, 200 minus 120, you will be getting 80 kg. And if 80 kg you write as 10x, so x will come out to be 8. So the option that you have to encircle, that will be equal to 8. So the option that you should encircle on your OMR sheet, that value should be equal to 8. I hope that you have got how to solve such kind of question. Let's go to the next question without taking more time. A simple integer type question we have discussed. So you have got an idea how integer questions will be and how they can be given in your examination. Let's go to the next question, question number 10. That's the last question of the exercise. It's an assertion region. That means that you have to choose 4 options A, B, C, D. Here I have not given you why when you have to choose A, B, C, D. There's less space, but I will tell you. A will be the right answer if both statement 1 and statement 2 are correct, and statement 2 is the right explanation for the statement 1. Statement number A, B will be the right answer if statement 1 is correct, statement 2 is also correct, but it is not giving the right explanation for statement 1. C will be the option if statement 1 is true, statement 2 is false. D will be the option if statement 1 is false, statement 2 is correct. Let's go ahead. Statement 1, the stream of water flowing at high speed from a garden hose pipe tends to spread like a fountain while when held vertically up, but tends to narrow down when held vertically down. If I write about this statement, if I show the scenario, if a pipe is there and a stream of water is actually coming out from here, so it says that it ejects in the form of a fountain. It emerges in the form of fountain. This is how its motion will be there. It will come in this way. And that's true also. You can see that that's true also, because you know why it happens. The velocity will be higher here. Understand, velocity will be higher here, and here as it goes, velocity will be reduced. If velocity is reduced from equation of continuity, the area will be more. If area is more, so area, that's why it's occupying more area compared to the area at the lower end. So let me show you here that here it's actually taking more area. Why? Because of equation of continuity. Higher the velocity, lesser is the area, lower the velocity, higher is the area. A1 V1 equals to A2 V2. So if V2 is less than V1, if we take velocity here as V2 and velocity here as V1, so clearly V2 will be less than V1, hence A2 will be greater than A1. So this is true. Statement 1 is true. Second statement, in any steady flow of an but tends to narrow down when held vertically down. We need to also comment on this. Tends to narrow down when the water is flowing in downward direction. It says that it will narrow down. This is what, yes, do we observe in this way? We do observe in this way, because what happens generally, let me show you in a different way so that you do not get confused with the colors. This is the pipe, the water ejects in the downward direction. So if the velocity is here V1 and velocity is here V2, quite simple, V2 will be more than V1, and if area I write A1 and A2, so So again from equation of continuity, A1 A V1 equals to A2 V2, and then if V2 is greater than V1, so you will be having A1 will be less than A2. Sorry, A2 will be less than A1. This is what we see. So statement 1 is true. It tapers down. It gets narrow as it moves down. It actually spreads. So it will be having higher area at the top. So statement 1 is true. Tends to narrow down when held vertically down. Yes, this statement is true. Statement 2, in any steady flow of an incompressible fluid, the volume flow rate of the fluid remains constant. Volume flow rate remains constant. Now see, to explain both the situation, I have used equation of continuity A1 V1 equals to A2 V2, A1 V1 equals to equation of A2 V2. This equation comes because in steady flow at any point volume rate flow is same. Then only this equation comes, as I have taken in the class also. So which option you have to choose? 1 is true, 2 is true, and 2 is the explanation of the first one. Directly it's not given about equation of continuity, but equation of continuity is hidden in this statement, volume flow rate. So you have to choose option number A as the right answer. Both are true and 2 is the correct explanation for the first statement. Hope you have got to know how to solve such kind of question. It is a very good question which has come in your previous examination. So you will be knowing that what kind of question an examiner may seek from you all. Have the understanding of concepts, do know how everything you have arrived at, so that if any logical question comes in the examination, you can easily answer them. So these are the first 10 questions that we have discussed for JEE Advanced Pattern. I'll meet you on the next class with some more concepts and with more examples. Till the time, thank you everyone. Wish you all the very best.